Hey guys, Professor Doney here again with another video for the vertical motion series. I appreciate the comments I've been getting, and yeah, I'm working on handwriting. I'm left-handed. I'm doing what I can, so hopefully you can understand everything I'm putting in there. So, alright, one-dimensional vertical motion. Why do we say it's one-dimensional? Because when we go up or we come down, it's going to be a straight line. Two-dimensional motion, which would be vertical and horizontal at the same time, would mean we would project it sort of like driving off a ramp or riding a bike off a ramp. You'd be going horizontal and vertical at the same time. That's two-dimensional motion, and that actually projects you or makes you land somewhere else. These are all, we will fall and land right below the drop zone, or when we throw something up, if it comes back down, it'll land right back where we threw it from. The idea of shooting a bullet up and having it come down or back into the barrel, pretty crazy, but that keeps it simple. So one-dimensional motion. Now, a couple different situations here, scenarios. The first one over here, I'll put a 1 here. Actually, let's change that color a little bit, see if we can get something a little better. There we go. One-dimensional motion, vertical. All right. This first situation is when the initial velocity in the y direction vertically means 0. We could call this a drop problem. I hold it in my hand, I release it, let it fall. I step off a balcony and fall down through a swimming pool. Something falls out of an airplane or helicopter, more precisely, that's stationary, we just drop it. So its initial velocity is 0. It falls out of our hands. Okay? Gravity then will accelerate. The force of gravity accelerates it at 9.81. The second type of problem we can have vertically is we throw something down. I use my hand. There's my hand. Nice. And I give it a little shove as I throw it down there. I don't drop my keys off the balcony. I throw them towards the ground. And what that means is the initial velocity in the y direction is not 0 because I'm giving it a shove or a push down. Alright, third type we can look at is when we just throw it up. Okay. Now, I forgot to write here, this is what we'd call a throw down problem. It's not a drop problem because we're actually giving a little push. A throw up would just be, well, going the opposite direction. We're starting lower, we throw it up, and it goes higher against gravity, so it tends to slow down. Alright, so the next type, or the fourth type, is I throw something up and it falls back down. Throw up and, well, that's supposed to be an and fall back down. Now really this is just a combination of going up, which is a 3, put together with a fall back down or drop, which is a number 1. So we could really look at this problem as two separate problems, and when we solve each one of these, we're going to look at doing just that. Now, in the book, understand, and in many books, what they're going to do is use those 3 equations to solve all of this. Alright, where are we here? 3 equations. V equals VO plus GT, V squared VO squared, plus 2G delta Y, and delta Y equals VT plus half G T squared. The book is going to apply these 3 equations to all of these, and we have to adjust the equations depending on how it is. It'll try to solve it all in one shot. What I'm going to do is break up each of these types and then show you how you solve them using these 3 equations, but keeping in mind why it makes it a drop problem, or why it's a throw down, why it's a throw up, and fall back down. So I'm going to really try to simplify it. Sometimes it takes an extra step in the solution. I just find it to be a little clearer for students to understand that. So the following videos, what we're going to do is look at each of these individually, do some sample problems, and show them how I find it a little cleaner or easier to solve. There are many ways to solve it, but this is just one way. So check back and we'll see how that goes.